All right, 4.9, antiderivatives. This is the fun stuff now. So everything you've learned about taking a derivative is done. And there's no more specific techniques on how to find a derivative. We've exhausted all of them, basically. Okay, so now we got to start going in reverse. Okay, differentiation is taking the derivative, right? So this is finding f prime of a given function f. Anti-differentiation, say that fast. Is now given a function f, we look for an antiderivative function cap f, whose derivative is f. Cap f prime is equal to f. So don't pay too much attention to the notation. Every textbook kind of uses it a little bit. But if you see a capital F, that means that was the original function. Okay. And if I'm finding an antiderivative of that, or a derivative of cap F, that's differentiation. An antiderivative of a little function f is equal to cap f, the antiderivative. All right, so if a function f is an antiderivative of f on an interval I, and we just saw this is just a rewrite of everything I just wrote. Cap f prime of f is equal to f of x for all x in I. It's just a formal definition of an antiderivative using this notation. And we can continue it on writing it symbolically. Cap f is equal to little f. And the derivative with respect to x of cap f of x plus c is equal to f of x, where c is a constant. Why do we add in a plus c? So derivative of cap f is f prime. Derivative of a constant is 0, right? So no matter what constant is out there, when I take the derivative, I have its antiderivative, cap f. Right? So if I say, let's just, quick example, y is equal to x plus 2. That's your function. Y is equal to x plus 5. What's the difference in those pictures? One's just higher than the other, right? It's the same slope, everything like that. They're parallel lines, right? All you're doing is just moving it up or down by that constant c. So the slope of the tangent line is exactly the same, no matter where that picture, how high it is or how low it is, right? So that's it. So we have to add in that constant c, and we can sometimes figure out specifically what that constant C is on certain types of problems, but not always. All right, so here's some examples. Let's go in reverse. F of x is equal to 3x squared. What is f? The antiderivative. I'm looking for some function whose derivative is 3x squared. How many of y'all taken calculus before? Don't answer the question. You may know how to do it really quick, but I just want you to think about it. Okay, if we were taking derivatives, normally we would take the power times the coefficient and then keep the variable and reduce the power by 1. Do all that reverse now. What is opposite of multiplication? Division, right? So we did power times coefficient. So now we're going to have something divided now, the inverse of the reverse of it, right? And then we were reducing the exponent to take the derivative. Now we're going to be adding there. Okay, so this is all you have to do is keep whatever you see there. So if I say 3x squared, I'm going to add 1 to the exponent and then divide by the new exponent. This is x cubed, right? What's the derivative of x cubed? 3x squared. So especially if it's just nice polynomials or simple terms where the power rule and reverse can be used, that is really easy. Also, all we're doing is just write what we see there, increase the power by 1, and now divide by the new power. So that's your tip and technique to find antiderivatives. So increase power by 1, then divide by new power. Is that the only antiderivative? The only thing that differs between antiderivatives is the constant. So all we got to do is just say, okay, so our cap f of x could be x cubed. Our cap f of x could be x cubed plus 1. Our cap f of x could be x cubed plus 100. It doesn't matter what that number is, so that's why we're just going to use an arbitrary constant. C. So our cap f of x is equal to x cubed plus c. So this is called a family of antiderivatives, okay, because that c has an infinite number of values, but the derivative of every one of those is always still 3x squared. All right, I'll let y'all do one example real quick. Say f of x is equal to, let's say 7x to the 5th power plus 9x cubed plus 10x squared minus 11x. And let's throw in one more. Plus, really nice 5-term polynomial, right? What is cap f? X. Each one of those terms, increase the exponent and divide by the new exponent. And simplify each term if it needs to be. But you can leave them as fractions, that's perfectly fine. All right, so we should have 7x to the 6th over 6 plus 9x to the 4th over 4 plus 10x cubed over 3 minus 11x squared over 2 plus what? What's the 5? It's 5x. Think about that's x to the 0, right? 5 is 5 times x to the 0 power. So you increase it by 1 goes to 1, 5x to the 1st over 1, right? And you can double check it if you want. Just take derivatives of all that, 6 times all of that. The 6's will cancel, reduce the exponent, goes down to a 5, right? So you just go back in our old-fashioned way of taking derivatives and you're back where you started. Walk in the park, right? Pretty easy. And then I forgot to add in something. What did I forget to put in? It's not necessarily wrong, but plus my c, right? In this case, I was saying c was 0, but I'll tell you this too. You notice I forgot to do it. I do it all the time too. If you forget to put your c on the test, I usually don't take off for it because technically you found an antiderivative. I'm not saying find the family of antiderivatives, right? So technically it's all right. But you'll see it sometimes it is required to put your c. We'll see that later today. All right, so this one, I have my f of x is equal to sine x. I'm trying to find some function, cap f, whose derivative is sine. This is where it's really nice to kind of memorize those tables, especially those trig function values, those derivatives of that. So you can go backwards and forwards and see this one is derivative of this, therefore this derivative is the original function. And if you can think about it, all right, well, sine and cosine usually have derivatives of either sine or cosine, right? Well, derivative of sine is cosine. Well, that's not it. That's saying derivative of cosine is negative sine. Well, that's pretty close. So that's all we're going to do here is say, okay, well, this is saying the derivative of cosine of x is equal to negative sine of x, right? So cap f of x has to be the opposite of the cosine of x. So we get negative of negative sine x, right? Gives us positive sine x plus your constant c. And always a good idea to check it. Negative of the derivative of cosine, negative sine x, plus 0, that makes positive sine x. Which is the f of x. So your trig function ones are a little tricky, okay? Because a lot of times the trig function ones aren't in exactly the format that you know they're derivatives of, so it's a little bit of manipulation sometimes. All right, so where this is leading, instead of having to say, find the antiderivative, you know math uses notation all the time, right? There's shortcuts, there's symbols and all that kinds of stuff, right? Saw that with summations, right? The ugly summations, we did that. We'll do some more of that later. So this is called indefinite integrals. Just a fancy way of saying find the antiderivative, okay? Here's your notation. A big, long, almost like an S, okay? It's just like a scroll. That's pretty much all it is. That's the integral. And then you have your function right after it. This is called the integrand. And then you have dx. And we saw dx earlier, last class. Dx is a differential. This means find the antiderivative of f of x, which will be equal to cap f of x, right? Plus some constant c, right? So we just got some fancy notation of saying antiderivative of 3x squared dx is equal to, we just did this one, 3x squared is antiderivative is 3x cubed over 3, which is x cubed, plus c. And you might be, why is that dx in there? It's coming. It is coming. All right, so I'm just going to write out what's called the power rule in reverse, in a sense, the actual format. You already know it, but just so you have it in your notes. the integral of, say, x to the p power dx is equal to x to the p plus 1 over the p plus 1 plus your constant c for p not equal to -1. The power rule does not work if you have, say, x to the -1 power. X to the -1 power is 1 over x, right? And so if I do the power rule, adding 1 gives 0 as a new power, then divide by that new power 0. You can't divide by 0, so that's why it doesn't work. However, you probably do know there is a function whose derivative is 1 over x. Let's see it again. Constant multiple rule. This helps to simplify down the function and then take its antiderivative. The integral of c times some function f of x in dx. You can take the c out, then times the integral of just the f of x dx. And then from here, a lot of times it's just nice little polynomials. That's going to be our whole goal, is to get the function after the integral sign written as a polynomial. That's going to be the easiest way to take the antiderivative. If it's not, then you're in Calc 2. A lot of times, yeah. The sum rule. So if you have multiple terms that can be represented as individual functions, maybe added or subtracted, you can break them up into separate integrals. So the integral of f of x plus a g of x all dx is equal to the integral of f of x dx plus g of x dx. And then if there's any constants in here, you can pull those out and so forth, and then use the power rules from there if you want it. So let's do an ugly mess. I want to find some functions whose derivative is that plus c. So that function plus c. Well, the first thing, like I said, a lot of times we're going to try to do a rewrite, so it's just a nice polynomial format. You can see we're dividing everything just by x squared. So division by a single monomial term in the bottom. Every term in the numerator is divisible by that, right? So I can rewrite this as 4x to the 19th over the x squared minus the 5x to the -8 over the x squared all dx. Simplify each one of those. You have division of like bases. That's going to leave 4x to the 17th minus -8 minus 2 is -10, right? So that'll be minus 5x to the -10 power all dx. Neither one of those have an exponent of -1, so the power rule works, right? So let's keep the 4. Let's go ahead and expand it all the way out just using these rules just to illustrate how this is you don't have to do this step, but just to show that this is 4 times the integral of just x to the 17th minus 5 times the integral, I forgot my dx, minus 5 times the integral of x to the -10 dx. So you don't necessarily need to do this step, but sometimes it makes the arithmetic easier. This will be 4x to the 18th over 18th plus some constant c for the first integral minus 5 times x to the Negative 10 plus 1, negative 9 over negative 9 plus some c. A constant plus a constant is still a constant, so I don't have to put two c's. I can just say that's just some new c. All right. So we have a final answer. Reduce it to 2/9 x to the 18th. This is minus a negative, so that becomes plus 5/9 x to the negative 9, all plus some constant c. All right, y'all try this one. Binomial times binomial. Always keep in mind, try to do a rewrite to get it look like a polynomial, right? It's much easier to find the antiderivative. All right, so just rewrite the binomial times binomial as 2x cubed. First, outer minus 5x squared, inner plus 2x, and last minus 5, all dx, right? So 4 terms, and then that evaluates out to 2x to the 4th over 4 minus 5x cubed over 3 plus 2x squared over 2 minus 5x plus some constant c, and let's simplify the fractions down. That's x to the fourth over 2 minus 5/3 x cubed plus x squared minus 5x plus c. Real? Pretty simple. Right, let's make it a little bit more challenging. See if you can recall some of your antiderivatives or your derivatives that give you antiderivatives. Let's say, what about sine x over cosine squared x dx? It's gonna take some playing. You look at that and you're like, I don't see any derivative I know of that is that, right? So I need to figure out, is there something whose derivative gives me this? Let's do some rewrites. So I'm gonna do a rewrite. Can I split that into two fractions being multiplied, perhaps? But 1 over cosine squared. That's where your identities, your trig identities come into play a lot. What is 1 over cosine? Let's do it this way. Can I do cosine squared? I could have did it in one step. Let's go ahead and just erase that. No, I lost my, there we go. There's my eraser here. I don't know. I'm not familiar enough with this program. Let's just do it just quick. There you go. How about if I do 1 over cosine x times sine x over cosine x? That's the same thing, right? And now I have an identity, say 1 over cosine x is secant of x. And what is sine over cosine? Tangent of x, right? And this right here is one of those nice derivatives. That's the derivative of what? Tangent. Is it? Secant x, tangent x is tangent x plus c. Other way around. That one's secant of x, right? Derivative of secant of x is secant x tangent x. So this is kind of where lots of memorization. And actually, the best thing I suggest you do, yeah, you memorize it, but put it in a table form, okay? And then refer to the table after you have it written down. Because just trying to keep track of it all in your memory, you're like, okay, that is very similar to tangent of x. But you got to start thinking, okay, tangent of x was secant squared of x. All right, so here's a table. This is what I suggest. Either you figure out a way to kind of memorize how to develop the table, and that's going to be the easiest way instead of just having to say, look at it and take a picture of it in with your brain. Unless you've got a photographic memory, and that's wonderful, but if you do, you probably can bypass calculus. You don't need it. But here are some tables of antiderivatives. All right, so we look at all the trig function ones because the power rule ones are the nice, easy ones to remember. If I have let's do derivatives and antiderivatives. Well, actually, let's do antiderivatives first. The antiderivative, or the integral of the cosine of x dx, is equal to what function has derivative of cosine? Sine. So this is sine x plus c. And then I'm going to make a line that comes down, and we're going to put table of derivatives. Because the derivative of sine of x is equal to the cosine of x. Back and forth, right? Next, we go to antiderivative of sine x dx. We did this one just a minute ago. This is negative cosine x plus c. Derivative of a cosine of x is equal to the negative sine of x. That's your basic, right? So it's just a positive antiderivative of positive sine x. So you got to insert that negative like we did earlier. Integral of secant x dx. This is your tangent of x plus c. The derivative of the tangent of x is equal to the secant squared of x. Cosecant squared is negative cotangent x plus c. The derivative of cotangent of x was the negative cosecant squared of x. Remember the negative cofunctions? That's how you remember those derivatives. Just of secant, tangent. Secant of x, tangent of x. Antiderivative is secant of x. That's one we just did, plus c. The derivative of just secant of x is secant squared of x. Secant of x, tangent of x. Lastly, just cosecant, cotangent dx. This is your negative cosecant. I'm sorry, just your cosecant. I'm looking at the wrong one. This on the other side's negative. So this is your cosecant. Actually, I just right. Negative cosecant of x plus c. The derivative of just cosecant of x is your negative cosecant CSC. Cotangent. So your antiderivatives of your trig functions, they're not necessarily always in the exact same format that you remember or memorize your derivatives of your trig functions. So there will be some bit of manipulation to get them into that format sometimes. For the most part, what you see is very, very little manipulation right now. That's where I say when you get to Calc 2, there's going to be a lot, so you got to recognize that. It almost fits this particular integral, but not, so there's going to be lots of techniques to get it into that. It's like the chain rule in reverse, okay, so, but there's no one particular method. You just got to kind of insert some algebra here, insert some there, and cross your fingers, right? Hopefully it works. Some more. That's not all of them. Number 7, the integral of e to the x dx. This one's really nice because the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus c. Antiderivative or integral of 1 over x dx. That's the same thing as saying x to the -1, right? We said we can't do that with the power rule because that'll become add 1, you get 0, divide by 0. That doesn't work. But there is a function whose derivative is 1 over x. This is the natural log of x. And I'll put an absolute value because that x has to be absolute value of that argument has to be positive. Our inverse trig functions. One over the square root of 1 minus x squared dx. That was the inverse sine of x. Number 10, inverse tangent. Its derivative, so its integrand is 1 over 1 plus x squared dx. That's your inverse tangent. I always find the inverse trig function ones are fairly simple to remember because they're very similar to each other. Just remember which ones has the negative. The inverse cosine would be the negative one, or similar as inverse sine. This one right here, 1 over, should be the absolute value. Well, that's fine, as it is. 1 over x times the square root of x squared minus 1 dx. This one was your inverse secant of x. Again, I just said we could do inverse cosine, inverse cotangent, inverse cosecant. They're the same of these, just put the negatives, right? So I'm not going to go ahead and write all those. So the derivative with respect to x of the inverse secant is that 1 over x times the square root of x squared minus 1. Let's just do a couple examples. And we'll look at what's called an initial value problem. Again, for this, use this table for a good while until you have them down pat and memorized. You should have most of them memorized with your trig functions. It's just the same thing now as going in reverse. Okay. All right, so this is going to be extremely hard to get it into like a polynomial format, right? Just because it's not over a single monomial term. That's the only time you can really do that and have term plus term plus term simplified with other exponents, right? But this can be rewritten. And this is where it's like, it takes a lot of just trial and error. It's kind of like seeing into the future. Where do you want it to be like? And you saw all those options. There's plenty of options, right? So let's just kind of see what we can do here by rewriting this perhaps like this. I see that I can factor out a 4 in the bottom, right? So let's just do that, definitely. Because if I can take these constants out, that makes whatever's left over more recognizable. So this is still 5x squared. Take out the 4 down here. That leaves 1 plus x squared dx, right? You see a 1 plus x squared? That's also in some other place we've just saw, right? 1 plus x squared is in the denominator for the antiderivative for, was that inverse tangent? Somewhere in there? So that might play into this in just a minute. 5 times all that numerator, 4 times all that numerator, that's 5/4 that comes all out, right? So we got x squared. Let's see, where was it? Right there. But this is 1 over 1 plus x squared. I've got x in there, x squared in the top. That's not 1. That's not helping out too much, but I can still keep on doing a little bit of rewrite. Now this is where the magic happens. Like, watch what I'm gonna do, and you're like, where in the world did you get this? Because I want a 1 to appear. So what I'm gonna do is add and subtract out a 1. So I'm gonna do 1 plus, say, x squared minus 1. That's the same thing, right? That's still equivalent. And now I'm going to start separating this into multiple fractions. But if I take the first 2 terms right there over the denominator, minus the last term over the denominator, that's as 2 fractions split up now, right? So I have 1 plus x squared over 1 plus x squared minus 1 over 1 plus x squared. Oh, there's the 1 over 1 plus x squared right there. Now can you see how easy it is to now finally take the antiderivative? 1 over x, let's rewrite it. 1 plus x squared over 1 plus x squared is 1, right? So all of this is the same equivalent expression. which this is 5/4, times the antiderivative of all this, antiderivative of 1x minus the antiderivative of 1 over 1 plus x squared, inverse tangent. Plus a constant c. You can leave it like that, that's perfectly fine. There's no need to distribute across. That's it. So that's a really, really good introduction to where you're going in Calc 2. Using those tables to figure out which one it looked like after doing lots of manipulation. Didn't it look like exactly, but with some algebra, you can manipulate it. Okay? All right, I can do this all day long, but really the only way you're going to get good at it is just throw you into the wolves. Okay? You have to practice. Okay, the easier ones again are those polynomial ones. Use the power rules. The trig ones, that's maybe as hard as you're going to see right now. Okay? Most of them will be almost very, very similar to what's in the table. So it's just a quick substitution. Maybe pull out a constant here or there or something like that, but nothing too crazy. All right. So one last problem. It's called an initial value problem. Now, some of you are all going into engineering field, right? So you can have so many maths that you can have to do. Calc 1, 2, 3, probably differential equations, right? So this is kind of an introduction to what's to come in differential equations, kind of real life scenarios of how things are used in the real world with where would you start and what would happen as you progressed along. Okay, suppose f prime of x, the derivative is given as x squared minus 2x, and some value for x is given. F of 1 is equal to 1/3. Find cap f of x that defines the initial value problem. This just gives really a specific equation. Instead of one specific antiderivative, you have a little bit more information to figure out what is c. And it gives you the specific function that behaviors this plan, this model, this scenario, whatever. So cap f of x is going to be the integral of, well, here's the derivative, x squared minus 2x dx, right? Which we know is x cubed over 3 minus 2x squared over 2 plus some constant c. We can find the exact value of c. Because f of 1 is equal to 1/3, so this is our f of x. I should put cap f of 1, right? Let's do that. This is the cap f. Can I say, don't pay too much notation, too much emphasis on the notation. Cap f of 1 and f of x, that's fine. F prime of x and little f of x, they're both all antiderivatives of each other. But we have this to be equal to cap f of x. I already have it, x cubed over 3 minus x squared plus c. Output is 1/3 for an input of x equal to 1. This gives our C. So these are really easy. That's 1/3. That's 1/3 on both sides. Minus 1 squared, 0 equals -1 plus C. C is equal to 1. So f of x specifically is our initial value problem. X cubed over 3 minus x squared plus C is now 1. Again, it varies by that constant. All derivatives, no matter what that constant would be the same. However, it's just specific to this unique situation. All right, any questions? Play around with this. Like I said, just definitely do the homework for this section. You really need to get the practice for this. You can read your notes 20 times and say, yeah, I have it. But until you actually work it and don't get it confused with taking the derivative, you're going in the reverse, okay? The derivative is staring at you. You have to figure out some other function that gives that derivative.